Hello everyone. I wanted to show a particular sum here that can be used to show a lot of really cool, interesting facts, specifically involved with the zeta function. And I don't know if I've quite seen the Basel problem proven in the way that I'm going to show here. I will say that this idea is very, very much inspired by a video I saw by this math channel called Figure It Out, which surprisingly doesn't have many views or subscribers. And I think actually the time we're recording this video, I have more subscribers than that channel, which is super surprising. And you'll see if you watch some of the videos that he has a lot more production, I guess you can say, involved. And the videos are kind of higher quality. But anyways, getting into this. So let's consider the sum from n equals 1 to k of sine of n times x over n. This is, of course, a function of x. Now, if you've seen something called Fourier transforms or Fourier series before, what I'm about to show can kind of be shown using that technology, if that makes sense. But I'm not going to do that. I'm going to show something else. I'll show the same result, but using a different idea, using a few different ideas that are more kind of closer to the ground, or a lot of what hopefully you've all seen before. But anyways, notice as k, the ending part of the sum, gets larger and larger, we get this kind of animation. And of course, as k goes to infinity, we start to see that we get these lines. In fact, this is known as a sawtooth type graph, or a sawtooth wave, I guess you can call it. It's not really a wave, but it's a sawtooth function. Now, I don't want to give it away necessarily, but I will say that if you were to create a line y is equal to mx plus b, let me write that here. You can actually toggle m and b, and you'll find out that b is negative, or m is negative, excuse me. So let's let it go between -1 and 0, just to get an idea of what it looks like. And then maybe not play, but we can like toggle it like around there. And yeah, it looks like it's about -1/2, which I believe actually is correct, but we'll see that in due time. And then b, it's not obvious what b is. You have to like play around with it a bit. It looked like 1.6 did the trick. Let's go between 1.5 and 1.6. Okay. Yes, you have to zoom in a little bit to see. In fact, as k gets larger and larger, you can actually see what value this is about. And if the number looks already familiar to you, maybe you already know what the result is here. But we'll actually show this in a pretty neat way. So let's dive into that. So how I'm going to begin this is by noticing that this really is the imaginary part of e to the ix over n. So I guess we can write that imaginary part of the sum from n equals 1 to infinity of e to the ix over n, e to the I nx over n, really. Now, of course, I'm pulling the imaginary part out of an infinite sum, so there may be some kind of fudginess there, I guess you can say. But you'll see quite a bit of things where you may question the steps, but it ends up being okay in the end. The result is definitely true. So the next thing I'm going to do is I'm going to actually just focus in on this guy for a moment. Let's write it down over here. And I'm going to take the derivative of this function with respect to x. So x is the variable here. So derivative with respect to x. Now derivative of e to the something is itself times the derivative of the power. And the derivative of the power, of course, is in. And of course, the reason why I want to take derivative is so that these n's cancel out. I is a constant, we can pull that out of the sum. Perfect. And I'm going to rearrange this slightly so it's something to the n. What comes to mind, of course, is geometric series. If we were to apply geometric series here, we have I times 1 over the first term in the sum, which is e to the ix when n is equal to 1, and then 1 minus the ratio, which of course is also e to the ix. Now, this is one of those weird steps. Is this allowed? Technically, this would only be allowed when the ratio in absolute value is less than 1. But if you know anything about exponentials involving complex numbers, e to the ix actually lives on the unit circle. So in the complex plane, the unit circle, every point on the unit circle as a complex number is of the form e to the I theta. it's supposed to be an e, sorry, e to the I theta, where theta is the angle that corresponds to that complex number. So in fact what that means is the distance from the origin of the complex plane is 1. So in fact the absolute value of anything in the form e to the I times something is actually equal to 1. So is this allowed? Well, technically not, but I guess I want to just kind of say that I'll make it be allowed. But one thing to think about is kind of extensions of infinite sums and if those results are true. So assuming this actually converges, it would converge to this if that was the case. What I'm trying to say is, like, if you consider something like the Grandi series, the sum from n equals 0 to infinity of negative 1 to the n. If you were to use the idea of geometric series here, this would be 1 over 1 minus negative 1, which is 1/2, which is clearly not true. But that's because this series doesn't even converge to begin with. So if this series we were looking at did converge, then that value would be true. In fact, one way you can maybe think about it is that the function 1 over 1 minus x is equal to the sum from n equals 0 to infinity of x to the n, only when the absolute value of x is less than 1. Otherwise, this function is perfectly valid for any other value except for x equals 1. But this series is not always valid. So one way to think of it is you have like an extension of that series. So long story short, I know that this series actually converges for particular values of x. I only want x to be in between 0 and 2 pi. We kind of saw that from the sawtooth graph anyways. But for example, when x is 1, there's a way of showing the sine of n over n, of the series of that anyways, converges indeed. So I know this converges. I know this converges because its real and imaginary part are cosine and sine. Which, by the way, I haven't written Euler's formula, but if you're curious, it's this. It's e to the ix is equal to cosine of x plus I times sine of x, which I'm hoping all of you have seen before. I would hate for this to be your first introduction of that, but anyways, there we go. So because this series converges, I'm going to apply derivatives, apply the series rule here for geometric series, even though it may not feel allowed, and then integrate back to get a value for something that I know indeed converges. And if you have an issue with that, I would love to hear your thoughts in the comments. But I do want to say that I have seen a few different ways of explaining what this sum is equal to that isn't exactly this way of showing it, but has essentially the same issue. It's just harder to spot. Anyways, I'll let you think about it, but let's look back at where we are. So we have the derivative of this guy is equal to this guy. So that means this sum from n equals 1 to infinity of e to the I n x over n must be the integral of this. In fact, let me bring that I front. Okay. I think so far so good. Is there any issue? Let me take a look at this. Right. So to actually take this integral, it's pretty easy to see. Derivative of the top, derivative of the bottom, excuse me, is kind of like the top. I want the top to be the derivative of the bottom to apply the natural log rule. Now, of course, we need a double negative to make that the case, just because derivative of the bottom is negative I e to the ix because of the negative in front of the e. Now, once that has been applied, this is the complex logarithm of the denominator. Now, I want to write ln, and if you expect me to write ln, I want to write ln, but there's a little bit of an issue, and it's because the inside is complex. So technically, we have to take the complex logarithm, which is just called log, which can be confused for logarithm. I want to talk a little bit, it could be confused for natural log, let's say. Let me talk a little bit about this because it's kind of an interesting conversation. So let's say you want to take the logarithm of z, where z is a complex number. There are a few ways of going about it. Let's say we want to find the real and complex parts. Let's call them a and bi, or a and b, a plus bi. Okay. If we exponentiate both sides, well, on one hand, you just get z. On the other side, you get e to the I, or e to the a, times e to the bi. Now at the same time, any complex number, z in particular, can be written in its corresponding polar form, which is its magnitude times e to the I times its argument, which is the angle theta that it corresponds to. So the way of viewing this is if you had the complex plane, you had a point here, and that's z. Its magnitude is the magnitude of z, which is just the square root of the sum of the squares of its components. So like for example, 3 plus 2i has a magnitude of the square root of 9 plus 4, which is 13. I'm just squaring the components. That's all that is. And the angle, of course, is this angle here. That's called the argument. Okay, that'll come up in a bit. Okay, so now what? Well, now if we compare these things, well, this must be equal to this. Okay, and b must be equal to theta. Of course, this is up to coterminal angles, so you can add or subtract a multiple to pi, but this ends up being true. I'll just say that it's the argument. So in fact, we know b is what is called the argument of z. Okay, what about e to the a? Well, e to the a is equal to z, like that. So if you want to get a by itself, it's log base e, which is ln of absolute value of z. Now, why are we allowed to use ln here? It's because the absolute value of z, or the magnitude of z, is a real number, and ln applies to real numbers. So log, the complex logarithm, log, I do mean log base e, but I'm taking it of a complex number. So to distinguish between the two, we write ln for log base e when the input is a real number, and log for logarithm base e when the input is a complex number. I know you've probably seen log for log base 10, but then in the context of complex numbers, that's what's done. Okay. Hope that made sense. That was a nice little discussion. So a, in fact, is ln of the absolute value of z. So now backtracking all of this from that explanation, we have that. Okay. Now remember, we are after the imaginary part. So what I want to do is I want to take the imaginary part of everything. Also, I probably should mention, we integrate this, we need a plus c. There are a few ways to show that c is 0. I could just tell you that, but I want to give you something to think about. And again, this is another one of those weird steps. But let's let x go to negative infinity. E to the negative infinity, after all, is 0. Now you may think, okay, e to the I times something is on the unit circle, so how can that ever go to 0? Again, something to think about. But I would think of this as e to the negative infinity, which is 0, and that to the I is 0. Is it? I don't know. Something to think about. But e to the negative infinity, let's just say, is 0. So this is the sum of all zeros, which is 0 on this side when x goes to negative infinity. Letting x go to negative infinity makes the e to the in 0. In fact, it makes the e to the ix 0. So that means this is 0, and we have log of 1. Log of 1, well, is 0, because e to the 0 is 1, of course, right? So in fact, this whole thing is 0, because we have log of 1. So 0 is equal to c plus 0. That means c is 0. Awesome. Again, a few different ways to think of it, but that's what I wanted to show. That's the way I wanted to show it anyways. So c is 0, so we don't need to write c. Awesome. Great. Now what? Well, now we want to take the imaginary part of both sides, so we can consider what we were wanting to consider at first. The sum for n equals 1 to infinity of sine of n times x over n. Perfect. So this is the imaginary part of this thing. Now we have a negative, so the negative will carry over. And remember, the imaginary part of this was the argument. Okay. So let me write ARG for argument. I want the argument of this thing. Now I want to talk about this for a bit. Again, I'm going to draw this picture just to show you what's going on. So let's say we have this complex number that has a real part of a and imaginary part of b. So this is the complex number a plus bi. That's how that looks, if you're curious how to graph those things. So the argument something like this. Now this, of course, is just in the first quadrant. Theta, again, is the argument. This distance is b in this right triangle we've created, and this distance is a. Really, it's the real part is a, and the imaginary part is b. So in fact, notice tangent of theta, right, is going to be opposite over adjacent, which is b over a. Okay. At the same time, this thing is 1 minus cosine of x plus I times sine of x. Why is that? Well, because, in fact, I meant to put a minus sign of I sine of x. Anyways, why is that? It's because e to the ix is cosine of x plus I times sine of x. The negative distributes, and that one in front makes that the case. Now notice, the real part here is this, and the imaginary part is this sign. In fact, it's negative sign, because the negative in front of the I. Okay, so in fact, what we can do is we can actually call this argument theta, and because it's the argument of that inside, we can actually consider now tangent of theta. So that's what I'm going to do. I'm going to consider tangent of the argument, which I'm calling theta. So from the image we have over there, tangent of theta must be what? It must be the imaginary part, which is negative sine of x, over the real part, which is 1 minus cosine of x. All right. Now, there are a few ways to go about this. In fact, I recently saw another YouTube video, watched a lot of math YouTube videos, where you can actually write anything in terms of tangent of the original input over 2. It's a pretty interesting idea. In fact, I believe it's called Weierstrass substitution. I'm not too sure, but it's kind of a take, more or less, on trig substitution, but kind of the other way around. Anyways, here's how I'm going to go about this. In fact, I'm trying to think of ways to describe it. What I want to do is I want to really want to take advantage of the double angle formulas. So what I'm going to do is I'm going to let x be equal to 2 times something else. I'll call it t. So x is 2t. There's negative sine of 2t, 1 minus cosine of 2t. Now the whole idea that I have is I want to, let me just think for a second here. Yeah. What I want to do is I want to write the left-hand, well, the left-hand side is already in terms of tangent. I want to write the right-hand side in terms of tangent as something else, and then I want to say that insides should be the same. Now again, I want this to be true for x being in between 0 and 2 pi. I think that'll fall out. So let's take a look. Now, if I use double angle formulas that we know, sine of 2t is 2 sine of t times cosine of t. Okay. What about cosine? Cosine of 2t, there's actually a few different ones we can use. That one in front makes me think that we want it to cancel out. If I were to replace it with 1 minus 2 sine squared of t, which I think actually is the one that I want to do, this is lovely, I think, because the 1s will cancel. See that? If we distribute the negative, these cancel, double negative is positive. And then the 2's cancel, look at that. And then we can cancel a sine as well. So I'm getting negative cotangent. Well, let me go one step at a time. Negative cosine of t over sine of t. Okay. I think we're okay. Almost where I'd like to be. Yeah, I think this is fine. Now, cosine over sine, there's a lot of cancellation there, so maybe you can like look through the details there. But cosine over sine, of course, is cotangent. So this is negative cotangent of t. And remember, t was what? Well, if x is 2t, then that means, well, t is actually x over 2. Okay. Now, there are a few ways to describe what I want to get at, but yeah, I guess we'll do, there's a lot of ways you can do this. Cotangent is odd, so you can bring the negative inside, I guess. I guess I'll just take this one step at a time. So this is cotangent of x over 2. Okay. Now cotangent is the co-function of tangent. If you don't know really how co-functions behave, basically you can replace the inside with pi over 2 minus the inside, and then the co-function gets replaced with its co-counterpart. So the co-counterpart for cotangent is tangent, right? It's the cotangent of tangent. So the cofunction of tangent. So in fact, this is tangent of pi over 2 minus x over 2. There's actually a really nice way of showing that with right angles, or right triangles, I meant to say. So for example, if you have the right triangle, and this is the input theta, then this right here must be pi over 2 minus theta. So what happens is adjacent and opposites, they switch. So tangent of theta is the same as cotangent of pi over 2 minus theta, because adjacent and opposites switch. You're switching perspectives of your angles. So again, something to think about. Now I want to bring the negative in so we can compare these tangents head on. So bringing the negative in, we can switch the difference. So we get x over 2 minus pi over 2. Which is really funny because we're going to get another sign change. We'll get back to pi over 2 minus x over 2. But right now this is okay. So are these equal? Well, if you remember how the graph of tangent looks, it looks like this. So I will say that theta is equal to the inside of the tangent on the right only when the inside is in between negative pi over 2 and pi over 2. So let's actually write that. So theta is indeed equal to this when theta is in between negative pi over 2 and 2. But in fact, that's this. And I wrote an equality. There should be no equality because of the asymptotes on tangent. Now, if you add pi over 2 to both sides, you get this. And then if you multiply both sides by 2, you get this. As desired. I only want x to be in between 0 and 2 pi, like I mentioned earlier. So this works fantastic. So there we go. We have theta. We have our argument. Now let's go back all the way above. And let's carry on. So we know now this is negative the argument theta, which was what? Was x over 2 minus pi over 2. And again, we'll have a double negative. So that's back to switching things around. Pi over 2 minus x over 2. That is what I wanted. Fantastic. So now let's continue and see some amazing facts that we can use this to prove. All right, so here is the amazing fact we just proved, which I showed a graph of at the very beginning. So in fact, yeah, that 1.57 number, that is pi over 2. And that 1/2 or negative 1/2 is indeed negative 1/2. That's the slope of this line. So very amazing. Now, of course, if x is 1, that sum that I told you actually converges, sine of n over n. Well, when x is 1 here, we see it's pi minus 1 all over 2, or pi over 2 minus 1/2, however you want to see that. It's kind of an interesting idea because it's similar to the alternating harmonic series. In fact, it kind of is that, but it's not alternating every other term. It's alternating kind of sporadically because of the way sine of n behaves as far as the signs go. But we're not going to get into that. What we want to do is we want to somehow get zeta involved. I want to try to find values of zeta. Now, I don't know if I've actually seen proofs that use this directly. They may use something similar that is from this. I've seen like proofs using Parsifal's identity, which isn't quite this, but it's within that realm of Fourier analysis. But anyways, I'm kind of rambling now, so as I always do. But what I'm going to do is this. I'm going to integrate both sides so that the denominator gains a power. Because remember, the antiderivative of sine is negative cosine, but you have to divide by the derivative of the inside if the inside is a multiple of x. And here we have a constant multiple of x. So we'll do that. We'll integrate both sides just like that with respect to x. So imagine the dx. Let me just include that, I guess. Okay. Now, on the left, what is the antiderivative of sine? It is negative cosine. We'll write the negative on the outside. And you divide by the number in front of x, which is n, so we get an n squared in the denominator, just like that. Okay, so now the antiderivative on the right side is pi over 2 times x minus x squared over 4, right? Plus a constant c. Now, what is this number c? There are a few ways of seeing what it is. Notice when n is 0, when x is 0, well, this becomes 1, and that's the Basel problem. That's sum from n equals 1 to infinity of 1 over n squared. That's zeta of 2. When x is 0 here, These both go away, so c must be equal to pi squared over 6. But I actually want to show that. I don't want to use that fact. I want to prove that somehow. So we need a different value for x. Which value for x can we use? So if x is, I'm going to see what happens if x is pi. Pi n is kind of interesting to think about, but it's kind of similar. I'm trying to think if that'll yield anything, or if that'll just give us. Because there are a few ways of doing it, but in fact, I will let x be equal to pi. So let's see what happens when x is equal to pi. So maybe I should say this. Sorry if I seem indecisive. But when x is 0, we get negative the sum from n equals 1 to infinity of 1 over n squared, because cosine of 0 is 1. On the other side, you just get c. So c is negative that value. Okay, that's the first thing. In fact, I want to know if I should just leave it like that or not. No, I'm not going to leave it like that. Let's actually just substitute it in. So c is equal to that, so let's just drag that over. Okay, that's the first thing. Now I want to actually figure out what that is using a different value for x. So now let's let x be something else. Now let's let x be pi, and let's see if that changes things or not. Now I'm going to notice something. I'm going to notice that cosine of pi is negative 1. So cosine of n times pi, because x is pi in this case, will actually start at negative 1 if you consider the sequence. It'll start at negative 1. Then you have cosine of 2 pi, which is 1. Cosine of 3 pi is the same as cosine of pi, which is negative 1, and it alternates like this. So in fact, because of the negative in front of the sum, if you bring that in, then you have alternating signs starting with a positive. And no, here it starts with a negative, but again, with a negative in front, counting that as well, will actually end up with the following. The sum from n equals 1 to infinity of negative 1 to the n minus 1 over n squared. And I know this is certainly true because of, well, we start with a positive after distributing the negative on the outside inside now. Okay, what else? Well, if x is pi, then we have pi squared over 2 minus pi squared over 4. 1/2 minus 1/4 is 1/4, so really that's just pi squared over 4, if you think about that, minus the thing we're trying to find. Now, as it turns out, we can actually connect these two. There's a lot of ways of showing what I wanted to show, but I kind of want to do it in general. I'm trying to think. Let's do it in general off to the side here. So in fact, I'll have to define a few things. So what I'm kind of dancing around is zeta of, usually it's called s, or s is a complex number, but here s is being treated as a real number. You can use x if you want, but I'll just write it as zeta of s just to be general. And this is the sum from n equals 1 to infinity of n to the negative s, or 1 over n to the s. That's fine. And at the same time, there's the Dirichlet eta function, so Riemann Zeta function and the Dirichlet eta function, which is the sum from n equals 1 to infinity of negative 1 to the n minus 1 over n to the s. So maybe I'll write this just for consistency like that as well. It looks a little better, I guess. Okay, so you'll notice that one is alternating, starting with positive, and the other one is non-alternating. Now you can talk about the regions in which these converge. It's kind of interesting. There's some connection between the two. In fact, what I'm going to do is I'm going to subtract them. What I want to do is I want to keep the even ones. So if you think about how this works over here, it starts with a positive. So that's positive 1 over 1 to the s, and then negative 1 over 2 to the s, positive 1 over 3 to the s. So the even ones are positive. Or sorry, the odd ones are positive. I want to keep the even ones though. So to make the odd ones negative, I'm going to subtract. I'll do zeta minus eta. So zeta of s minus eta of s is equal to, there's a nice way of writing this. Look, check this out. We have 1 minus negative 1 to the n minus 1 all over n to the s. That's kind of interesting. Now let's think about what this is. What is this? So this is when n is, let's see, when n is odd, negative 1 to the n minus 1 is going to be positive 1. And then 1 minus 1 is 0. So this is 0 when n is odd. And what about when n is even? Well, negative 1 to an odd power, because when n is even, n minus 1 is odd, is negative 1, and then 1 minus negative 1 is 1 plus 1, which is 2 when n is even. So in fact, what we'll do is we'll kill the odd terms, because there's 0, of course, and to include the even terms only, we can replace n with 2n. And the top is 2 in that case. Looks a little ugly, but that's supposed to be an s power. There we go. Now, what you can do is you can actually extract zeta back out of this. Let me show this. So if you pull that 2 out, and also pull the 2 to the s out, you have this n to the s in the denominator left. And in fact, this coefficient in front you can write as more compactly as 2 to the 1 minus s, and then that's zeta of s. So you have this really awesome formula that is this is equal to this. And in fact, if you switch the positions of eta and zeta, take an eta by itself, this is a really nice way of writing it. You get eta of s is 1 minus 2 to the 1 minus s all times zeta of s. This is an amazing formula that allows you to connect zeta to eta. Okay. Perfect. And that's kind of what we have, because really, going back here, this is zeta of 2, which we don't know right now. I mean, it said what the value was earlier, but we don't know what it is right now using this, this narrative, right? This is eta of 2. And we just found out a connection between the two. We want to find zeta of 2, so I'll say this is equal to, over here, this is equal to what? This is 1 minus 2 to the 1 minus s. That's 2 to the 1 minus 2, s is 2 in this case, times zeta of 2. Perfect. So that's equal to pi squared over 4 minus zeta of 2. Fantastic. Can we solve for zeta of 2? I think we can. Right. Notice this power right here, 1 minus 2, that's negative 1. 2 to the negative 1 is 1 half, 1 minus that is 1 half. So we go 1 half, zeta of 2 is equal to pi squared over 4 minus zeta of 2. Let's add this guy to that side. Adding those two, well, 1 plus 1 half is 3 halves. I think we see it already. We see it? Getting excited. There we go. Multiply both sides by 2 over 3. And there it is. 2 over 12 is 1 over 6. Or 2 goes into 4 twice. Bam. How awesome is that? So we're able to prove the Basel problem using essentially the that sum. The sum for n equals 1 to infinity of sine of nx over n is equal to pi over 2 minus x over 2. Now it doesn't end there, does it? I don't think it does. So I'm going to try to take this a little bit further, and let's see what happens. So let's consider now, and I have to kind of go back up a bit. So let's get rid of this. So we found out that zeta of 2 is pi squared over 6. That's all of this jump kind of gave us. We had to plug in a few values for x, and there we go. Pretty cool. And we box this. All right. Now what? Well, now I guess we can keep going. Maybe let's integrate again and see if we can find other values. In fact, could we keep going forever and find all values? Now, something kind of happens when you get to the odd ones, and you'll kind of see more or less the reason why there's no exact closed form for it. That's kind of hard to say that that is indeed the case, but yeah, that is kind of the case. I say kind of because it hasn't been proven mathematically, but it appears to be the case that for odd values, zeta of an odd number doesn't have a closed form. But anyways, that aside, let me move some things around just a little bit here. So let's multiply both sides by negative 1. Now let's integrate both sides with respect to x. Perfect. Antiderivative of cosine is positive sine. But again, you divide by another n. So that's n cubed. On the other hand, we have negative pi x squared over 4 plus x cubed over 4 times 3 in the denominator is 12. And then the antiderivative of this is that, and then plus a constant. So this is what I was talking about earlier, why the odd ones don't really work out, is because c ends up being 0. So we can't get a new value, unfortunately. And it's 0, c ends up being 0 because when x is 0, the sum on the left is just 0. Cosine of 0 is 0. Everything else is 0. And in fact, right, I kind of slightly messed up. The antiderivative of pi squared over 6 is itself times x. So now, there we go. Now we get 0 is equal to 0 plus c, so c is 0. So we can just cancel that plus c out, because, yeah, it ends up being 0. Okay. Now, there's a pretty interesting fact here that I kind of want to mention, and that's when you plug in n to be pi over 2. Getting back to that figure it out video, he actually shows this, which is really nice. But notice the sequence of sine of n times pi over 2, that is 0 sometimes actually. So when n is 1, sine of pi over 2 is actually, it's actually 1. And then sine of 2 pi over 2 is sine of pi, which is 0. And then negative 1, and then 0, and then 1, and then 0, and then negative 1. You see it's 0 every other one, and then it alternates every other one. So it alternates starting with positive 1 for the odd ones, and then is 0 for the even ones. So one way we can actually write this out is we can replace sine of n pi over 2 with the alternating negative 1 to the n minus 1 because we want it to start with a positive, over, instead of n to the third, I'm going to write 2n minus 1 to the third. Why it's minus 1 is because I want these to be odd numbers starting with 1. And when n is equal to 1, 2 times n minus 1 is equal to positive 1. So there we go. Now remember, we're letting n be pi over 2. So here we'll get negative pi over 4 times pi over 2 squared, which is pi squared over 4, plus, let's see, that's going to be, well, pi over 2 cubed is pi cubed over 2 cubed, which is 8, and 8 times 12 in the denominator is 96. Okay, and over here we have pi squared over 6 times pi over 2. So everything's multiplied by pi cubed if you look at that in the numerator. That's all pi cubed. Perfect. Now, as far as numbers go, we have negative 1 over 16. Pi is a number, but you know what I mean. As far as the fractions go, rational numbers. We have negative 1 over 16 plus 1 over 96 plus 1 over 12. And if you find a common denominator, maybe we can do this. So 96 we got from 8 times 12, right? And this is in fact 8 times 2, but 8 times 12, well, here's a nice thing actually. 8 times 12 is, I guess 16 is in there somehow. So yeah, it's 8 times 2 times 6, which is 16 times 6. So in fact, if you multiply this by 6, top and bottom, you get 1 minus 6 over 96, which is negative 5 over 96. Now, how can you get 12 from that? Well, we just saw that, we just saw that 8 times 12 is 96. So in fact, multiplying this by 8 top and bottom gives you that. But that, in fact, is 3 over 96, which reduces to 1 over 32. That's what I wanted to show. So in fact, all in all, this is equal to, let me get rid of this, pi cubed over 32. Which is pretty close to having a value for zeta of 3, but this is alternating odd ones. You can't actually compare this back to zeta of 3 like we did with eta and zeta, because this is not actually eta of 3, even though it kind of looks like it because it's alternating. I don't want to get into the details, but long story short, it's because we have only the odd terms. The eta function is alternating with all of the terms, not just the even ones or the odd ones, but all of them. So it's something to think about. Okay. There we go. So that was an interesting result. But now can we actually do this one more time and actually find a zeta of 4? Well, let's try it. And this will be the last one, by the way, because I know this video is way too long. But we're going to integrate both sides with respect to x. Antiderivative of sine is negative cosine. We got an n to the fourth in the denominator. Great. The antiderivative of the other side is let's see, we get negative pi x cubed over 3, but with the 4 in the denominator, that becomes a 12. This is x to the 4th over 3 times, 4 times 12. That's going to be 48. And then this is going to be pi squared x squared over 2 times 6 is 12, and then plus a constant c. So I have a hunch that when we plug in x to be 0, since cosine of 0 is 1, we'll get our zeta of 4 value. So let's see what happens when x is equal to 0. We get negative zeta of 4 on one hand. All of the other terms have x, so those cancel out. And then we get c. So c, in fact, is negative zeta of 4. Let's include that here. Perfect. Now, much like we did earlier, we want to find what happens when x is equal to pi. So when x is equal to pi, well, cosine of pi, again, is alternating in sign. It starts with -1, though. So when you bring the negative in, it's the exact same thing we saw for zeta of 2. The super similar calculation. We get this. In fact, thinking more about this, this is just eta of 4. What about all the other numbers? So, I mean, the calculation isn't too bad. You'll notice that everything has a pi over 4 in the numerator. So this just becomes pi over 4. And in fact, what's more interesting is that we have -1 over 12 and +1 over 12, so those cancel. So in fact, quite literally, this is just pi over 4, or pi to the 4th, excuse me, over 48 minus zeta of 4. Perfect. Now remember, eta is 1 minus 2 to the 1 minus s, which is 4 here, times zeta of s, which is 4. I'll add actually, there's a few ways of doing this, but what I want to do is I want to add this to the other side like that. But because we're adding zeta of 4, we can factor it out, and what ends up happening is you add a 1 in the parentheses. So that 1 will change to a 2, in fact. That's a nice way of seeing this. And of course, 1 minus 4 is -3, so that's 1 over 8. 2 minus 1 over 8. You can't think of 2 as like being 16 over 8. 16 over 8 minus 1 over 8 is 15 over 8. So we have this times, not 15 over 8, but I guess 8 over 15. Whew. Okay, now 8 goes into 48, well, 6 times, and 6 times 15 is pi over, is 90. So pi to the 4th over 90. And in fact, this is the value of zeta of 4. Awesome. Can you keep doing this? You can. Did Euler do it like this? No, I don't think he did. In fact, from what I know, he used that well-known way of finding zeta of 2 by considering factorization of sine of x over x and comparing that with the Maclaurin series expansion of sine of x over x. And you can repeat that process kind of there's a lot of videos to explain it. In fact, if you look online, you can find a lot of proofs involving that. I haven't quite seen this though. I'm sure there's documents that show this, but I just maybe haven't looked around too much. Anyways, there we go. That's what I wanted to show you. Hope you enjoyed the video. Please share it with people that you know, because I want to get exposure. So anyways, really appreciate it. Like I said, Figure It Out is a great channel that deserves watches. And yeah, I'll post links to his video and channel down below. Anyways, thank you all for watching. I hope you really enjoyed the video. Please give it a like and subscribe if you really like this content. If you have ideas or anything in particular you want to see, please let me know, because I want to start creating more videos. Anyways, thank you for watching. Take care. See you next time.